Thank you very much, Roger. Thank you, John, for the introduction. Well, good evening, everyone. A pleasure to be here. As John mentions, I follow in illustrious company after Stephen Hawking and Carlo Rovelli. I should also mention that about 12, 13 years ago, I set up an annual lecture series for my physics department at the University of Surrey, and of course Roger Penrose was the inaugural speaker at that series. I recall our seminar organizer rushing around to find an overhead projector for Roger's famous transparencies with his drawings of black holes, event horizons, and light cones. So it's a pleasure to be here, pleasure to be giving this lecture this evening on quantum biology. I see there's a mixed audience here in terms of expertise. Well, I'm guessing there is. I hope there's going to be something for everyone. I think those of you who don't have a strong background in science, there should be enough for you to follow the story and why this is a fascinating new field, but hopefully there'll be some nuggets from my own recent research which will satisfy those who are more physically or mathematically inclined. Well, let me just move that cursor away from the screen. That bugs me. There we go. Okay. Normally when you learn physics, when you do science at school, it tends to be in these silo subjects of physics, chemistry, biology. And of course, once you go on to study science at university, you may choose to do an area of science that's at the interface between this, biochemistry, physical chemistry, or so on. The subject of quantum biology, which I will define in a moment, I guess sits somewhere in the middle, because it requires expertise in physics, whether it's biophysics or theoretical physics, quantum mechanics, computational chemistry, quantum chemistry, but also, of course, molecular biology. Now, why quantum biology? What's so interesting there? Well, of course, and many of you will know that this is a subject that goes back many years, back to Schrödinger's famous book, What is Life, in the 1940s. But just simply looking at the scale of objects in our world, starting from something like a tennis ball, which we would be able to describe using Newtonian mechanics. You know, the forces acting on the ball, how it spins, its angular momentum, the way it bounces, the way gravity it gives it a parabolic arc through the air. Newtonian mechanics is enough to describe it. But as we go in power orders of magnitude smaller and smaller and smaller, we get down to scales where Newtonian or classical mechanics breaks down. And we need a new mechanics to describe objects in that world, namely quantum mechanics. Now, of course, it's rather vague where we have to give up on classical mechanics and use quantum mechanics, but certainly down at the nanometer scale, a billionth of a meter, one would expect quantum effects to start to kick in. I've deliberately put in objects and molecules of life here, right down to the double helix of DNA, to show that the building blocks of life fall in this sort of rather vague area between classical and quantum mechanics. I've spent most of my career, before I got involved in this area, as a nuclear physicist. So trying to study nuclear reactions and developing ideas in quantum scattering theory to determine the structure of atomic nuclei. Now, if you remember, an atomic nucleus is made of protons and neutrons. A nuclear physicist doesn't dig inside the protons and neutrons in general, so we're not that interested in the internal quark structure of those particles, but the way the protons and neutrons arrange themselves in a nucleus according to the rules of quantum mechanics. So I was very familiar with the need to use quantum mechanics to describe atomic nuclei. If we could get away with not using quantum mechanics or having some sort of hybrid, what's called semi-classical mechanics, then we saw that as a triumph, because that tended to sort of, make the calculations easier. But scale back up to the nanometer, and we are at structures that involve atoms and molecules, albeit bonded together in quite complex structures, that nevertheless one might think should obey the rules of quantum mechanics. Well, of course, physicists and chemists are used to using quantum mechanics. We're coming up in this decade to celebrate the centenary of the development of the theory by the likes of Niels Bohr and Werner Heisenberg and Schrödinger and others. So we've had a long time to get used to it. In fact, in physics, by the second half of the 20th century, we had pretty much figured out the building blocks so far of matter, of our universe. The quarks and leptons and the force-carrying particles, the photon and the gluon and so on. We wouldn't be able to have determined the building blocks of matter, these fundamental particles, without having an understanding of the quantum world. Likewise in chemistry. This is a modern periodic table. By modern, I mean if you look, so I'll just shine my pointer over here, element 118, oganesson. That's the heaviest synthesized element. It's created just for a fraction of a second in a nuclear accelerator. So you're not making bulk material, you're making individual atoms of this new element before they radioactively decay away. An interesting point, by the way, oganesson is named after a nuclear physicist, not a chemist, a nuclear physicist by the name of Yuri Oganessian. And he's the only living human today who has an element named after him. There are many other elements named after people who are no longer with us. When Mendeleev first created the chemical, the table of elements, of course, there were only roughly half the number that we have today. But what's interesting is that this classification, the structure, the order of this periodic table has pretty much remained the same, based on the chemical and physical properties of all the elements that we find. But we can only understand why these elements are classified and ordered in this way with an understanding of the quantum world. Because it's the rules of quantum mechanics that tell us how electrons arrange themselves in atoms and give these elements their properties. So, quantum mechanics is the bread and butter of much of physics and chemistry, and we've got used to it. What we haven't got used to yet, I would argue, is what it all means. This is the quantum skier. See, the tree looks fine. There's no reason to think that he can't father children at some point. And yet you see something like that. Of course, this is a cartoon, but if you see something like this on YouTube, you'd guess there's some trickery going on, of course. This sort of trickery is essentially what happens in the quantum realm all the time. It's counterintuitive. The mathematics of quantum mechanics works, and it's fine, it's powerful, it's led us to this great understanding and developing the whole of our modern world, really, certainly modern electronics. But at its heart, we are still struggling to figure out how it does, or particles do what they do, going in two directions at once, or having sort of behaving as though they're spread out over a larger volume until you observe them and force them to make up their minds what they want to be doing. The famous Schrödinger's cat in the box. But biologists, by and large, have avoided quantum mechanics. I'm being deliberately cruel here, because biologists don't use balls and sticks models anymore. They have computers. But, but the idea here is that here you have atoms bonded together. The grey are the chemical bonds. So you can see black is carbon, white is hydrogen, oxygen and nitrogen. The elements. So this is an organic molecule, the elements of life. Of course, I'm going to have to explain why I think life is special and any different from inanimate matter. Of course, these days, say we have computers and one can simulate the vibrations of the various atoms in a large molecule. This is a protein made of 100,000 atoms or more. What's interesting here is there isn't much quantum mechanics involved. Yes, you might need certain basic quantum rules to describe the chemical bonds that hold the atoms together, but these are still classical balls bouncing around. Where's all that fuzziness? Where's all that probability? Where's all the wave-like nature of matter that we hear about in the quantum world? The problem is that biologists and molecular biologists haven't needed quantum mechanics. Molecular biology and genetics really evolved and developed going back to the 1930s, when quantum mechanics was still very young. And at the time, a lot of quantum physicists, actually a lot of quantum physicists became molecular biologists. But many of them sort of strode out of their labs and offices flush with the success of having been able to describe the physical world using their new equations of quantum theory. Thought they'd give biologists a helping hand. You know, maybe you need our help in explaining the building blocks of life. And biologists said, no, thank you very much, but we're doing fine. And by and large, they have been doing fine. But there has now emerged this new area of quantum biology where it looks like we may need, in certain features inside living systems, to describe what's going on using quantum mechanics. If we think of quantum physics as the sort of the foundation of physical reality of our universe, then clearly the rules of quantum physics would lead ultimately to organic chemistry. They're made of atoms, and quantum physics describes atoms. Quantum chemistry, scaled up in complexity, is molecular biology. Molecular biology gives us life. So naively one might say, well, of course life needs quantum mechanics. But then so does everything else, right? Everything's made of atoms. Why should life be treated any differently? And we talk about life needing quantum mechanics when any other system, inanimate matter, is also made of the same building blocks that behave quantum mechanically at that fundamental level. And so, what is it that quantum biology, what distinguishes it from what distinguishes life from non-life in terms of the need for quantum mechanics? Well, we tend to talk about non-trivial quantum effects, by which I mean things like long-lived quantum coherence. One of the arguments is that, one of the challenges, for example, facing us in trying to build a quantum computer, which distinguishes it for itself from classical computers made of, so quantum computers made of qubits. Things can be doing two things at once, not 0 and 1, but 0 and 1 at the same time. One of the challenges, of course, is that quantum effects are delicate, they're ephemeral, they dissipate very quickly in what's called decoherence. So you want to hang on to them for as long as possible. Inside a living cell, there are thousands of biochemical reactions taking place. It's a busy, hot, messy, noisy, complex place. And a back-of-the-envelope calculation will tell you that quantum effects would disappear very, very quickly, far too quickly for them to play any role in biology. Not necessarily. So long-lived quantum coherence is something you're looking for. Quantum superposition, so a particle can exist in more than one state at the same time, having more than one energy, for example, or be in physically different locations at the same time. Going around trees, like the quantum skier. Quantum tunneling. Again, something that physicists and chemists have been very familiar with, going back a whole century. Quantum tunneling, the idea that particles can sometimes behave like waves, and a particle can actually pass through an energy barrier, a force field, a bit like a ghost or a phantom passing through a solid wall. Something that if we saw in our everyday life, we'd be amazed by, but that happens all the time in the quantum world. I always say it's a bit like you're having to kick a ball up a hill. You have to give it a hard enough kick to get it over the brow of the hill, over to the other side. And if you don't kick it hard enough, it'll roll back down again, every time. In the quantum world, you can kick it and need only go up halfway up the hill, but there's a certain non-zero probability that it will then disappear and reappear on the other side and roll down the other side of the hill. It sounds like magic, and when explained to a non-scientist, they tend to think, well, that sounds silly, don't you? Right? Go back and think a bit harder, because that surely is impossible. But it's what happens, and we know that happens in the quantum world. In fact, quantum tunneling is the reason we are here, because it's the reason the sun shines. The process of thermonuclear fusion that gives the sun its energy, its light and heat, is because light atomic nuclei are fusing together to form heavier ones. The first step in that process is two hydrogen atoms, or rather two hydrogen nuclei, protons, fusing together. But if you remember, protons are positively electrically charged, and so they will repel each other. They can't stick together unless they get close enough together to feel the much stronger, what's called unimaginatively, the strong nuclear force. But they can't get close enough to feel the strong nuclear force because of the electrostatic repulsion between them. But because they can quantum tunnel through this repulsive barrier, you can think of one tunneling through the barrier to get close enough to the other. They can get close enough. There's a probability they can get close enough to stick, to fuse in this process of nuclear fusion. So quantum tunneling is something we know a lot about. It was the earliest ideas of quantum tunneling came about in understanding radioactive decay, how a radioactive nucleus can spit out an alpha particle. The alpha particle also has to overcome an energy barrier. So there's a certain probability that it can escape. Okay, and then quantum entanglement. Now, quantum entanglement is one of these weird, it's been regarded as a weird mechanism. Famously, you may have heard that even Einstein didn't like it. He called it spooky action at a distance. The notion that two separated particles were still needed to somehow be described as one quantum system, one state, which means that if you observe or measure one of the particles, somehow that's going to change or affect the properties of the other one. Well, quantum entanglement we're now becoming more familiar with and discovering that it's actually possibly one of the most fundamental notions in quantum mechanics. Entanglement is something that should be taught at undergraduate level. I don't know how many other physicists in physics departments teach ideas about entanglement at undergraduate level. They're probably still teaching the basic, for the physicists in the audience, the one-dimensional Schrödinger, time-independent Schrödinger equation, square barriers and square wells and transmission and reflection curve. Boring, boring stuff. They don't mention the measurement problem, they don't mention quantum entanglement, they don't mention decoherence, and they blinking well should. Right, so these are the non-trivial. What is trivial then? Well, the trivial quantum mechanics is simply the discreteness of electron orbitals that give rise to the properties of chemical bonds, for example, how electrons arrange themselves between atoms when they're bonded together. This is somehow somewhat more interesting, these effects. Okay, so how did quantum biology start? Well, actually, it goes all the way back to the early 20th century. There were successes in quantum mechanics in the 1920s, but there was also an interest in what is called organicism. So basically, there were two schools of thought in biology back at the turn of the 20th century. You had reductionism, the idea that something was simply the sum of its parts. You take it apart and you should be able to, to its building blocks, you should be able to put it all back together again. The other side, you had vitalism, which was sort of almost a non-scientific idea that somehow there was a spark of life. There was some magic pixie dust you could sprinkle over inanimate matter and endow it with this property we call life. In the middle was organicism. The organicists said there's something mysterious about life that can in principle be explained, but it either requires a different way of approaching what we currently understand as the laws of physics and chemistry, or we may need new laws of physics and chemistry. It's not magic, right? It's not vitalism in any sense, but there's something more to life that distinguishes it from inanimate matter. And that led to, when quantum mechanics was developed, people started to wonder whether quantum mechanics was that new principle that could be applied and explain life. Niels Bohr, founding father of quantum mechanics, I guess, inspired many people. Max Delbruck started off as a nuclear physicist, ended up being a molecular biologist. Bohr gave a lecture in 1929, and he says the following: "Before I conclude, it will be natural at such a joint meeting of natural scientists to touch upon the question as to what light can be thrown upon the problem." Bohr was awful at explaining things, very obscure. light can be thrown upon the problems regarding living organisms by the latest developments of our knowledge of atomic phenomena, by which he means quantum theory, which I have here described. Basically, he's saying, can we learn something about what makes life special by using some of the ideas from quantum mechanics? So he was just throwing it out there for people to think about. And some physicists took that up. One in particular was Pascal Jordan, not one of the people that we tend to remember as the founding fathers of quantum mechanics. Think of, if you've seen the film Oppenheimer and the list of great physicists who are working on the Manhattan Project. And even those who aren't there, we know of Schrödinger and Heisenberg and Pauli and Dirac and Fermi. Pascal Jordan, well, he published a paper in 1925 with Max Born in Germany, in Göttingen, and then they were joined by the young genius, Werner Heisenberg. So these two papers on quantum mechanics, or what became known as matrix mechanics, essentially laid the mathematical foundations for quantum mechanics in the 1920s. I show these to emphasize Jordan's quality as a physicist playing with the big boys. Well, it was Jordan who arguably published the first paper on quantum biology. Bohr had developed this idea of indeterminism and complementarity, ideas almost relating to Eastern mysticism. Jordan wanted to apply some of Bohr's ideas inside living systems to try and explain what's special about life. You'd think that, therefore, he would be renowned and goes down in history as the founding father of quantum biology, going back to the early 1930s. There was, however, a rather serious problem. Jordan was a Nazi. And I don't mean that I'm keeping my head down, not saying anything, sort of Nazi in Germany in the 1930s. No, he was a fully paid-up fascist. And he tried to incorporate some of the ideas from quantum mechanics into his political ideology as well, and vice versa. And so, of course, after the war, he was completely discredited, and with him, to some extent, went quantum biology, because he was the sort of the flag waver for quantum biology. Quantum biology as a field had nothing to be ashamed of. It's not like eugenics, right? It was a serious attempt to try and look at whether quantum effects play a role in biology. But of course, it lay dormant for a while. Well, almost. Because another one of the founding fathers of quantum mechanics was Erwin Schrödinger, and he wrote this famous book, What is Life, in 1944. And in it, he says this: the living organism seems to be a macroscopic system, so, not quantum, but large in terms of its complexity and size, which in part of its behavior approaches purely mechanical as contrasted to thermodynamical behavior, to which all systems tend as the temperature approaches the absolute zero and the molecular disorder is removed. Basically, what he's saying is that there are certain materials that if you cool them down to near absolute zero, right, 0 degrees Kelvin, minus 273 degrees Celsius, just a few degrees above absolute zero, certain quantum effects can kick in. Superconductivity, superfluidity. What's happening is that because it's getting so cold, we're calming down the thermodynamic chaos and movements and vibrations of the molecules and atoms that make up that material structure. So when you calm them down, these delicate quantum effects can then kick in. They don't get washed out by thermodynamics. And Schrödinger was saying the order, the structure inside living systems is reminiscent of inanimate matter near absolute zero, where quantum effects play a role. So do quantum effects play a role in the structure and order of life? So the point is, we are in some sense like steam engines. We need energy, what we call useful low entropy energy, as food. Like you shovel coal into a steam engine and that coal is turned into useful work. Steam engine can move. Well, we also need food, metabolize it, and that gives us energy to live and to maintain our living state. If we don't have the fuel, we die. But we're more than that. And so, Schrödinger's point was, can life somehow sort of reach down beyond the thermodynamic chaos, down to the discreteness, the order, the structure of the quantum world. Well, nothing much happened after Schrödinger's. I mean, admittedly, What is Life was incredibly influential. Crick and Watson both stated that they found it very inspirational in their research. But nothing much happened, really, for several decades. Well, it happened slightly before this came out, but this is the front cover of the journal Nature. It depicts what became the poster child of quantum biology, the bird, the European robin. It's an article by the science writer Phil Ball in 2011. The idea of the robin is that it's one of the creatures that we know has something called magnetoreception. It can sense the Earth's magnetic field. We know that there are lots of animals that can do that, including insects and you know, the monarch butterfly and so on. But it's the European robin that got picked up and studied carefully and linked with quantum mechanics. It was studied by an ornithology husband and wife team. They published their work in the journal Science in the 1970s. What they would do would be, they knew the European robin. So unlike the British robin, which is sedentary, which stays on the British Isles all year round, the European robin that spends its spring and summer up in Northern Europe, in Scandinavia, migrates every autumn down to the Mediterranean. And as we know with migratory birds and marine mammals, they have lots of tricks that allow them to find their way, whether it's having a map of the stars or following a sense of smell or whatever. Well, the European robin also uses this magnetoreception. It can sense the Earth's magnetic field, a very weak magnetic field. How can that influence a living organism? Well, they confirm that it does. They would capture these birds in mid-migration, stick them in these funnel-like chambers with a sponge with ink at the bottom, so when the bird is down on the base of the funnel, it gets his feet covered in ink, and then blotting paper around the sides. So as it tries to escape from this trap, it automatically tries to continue its migratory journey in the right direction. And so you'll see many more footprints in one direction, on one side of this funnel, aimed down towards the direction of that it wants to fly down to the Mediterranean. They can then put magnetic fields around these traps, something called Helmholtz coils, that can have the same magnetic field strength, but opposite polarity to the Earth's. So they cancel out the Earth's magnetic field. So the birds don't sense any magnetic field, and they fly around in all directions, and you see sort of footprints all around evenly. So anyway, that was beyond sort of doubt, but what was the mystery was, where is this chemical compass? And by the time that Phil Ball wrote his article in Nature, the leading theory, and to this date it's the only theory we have, doesn't mean it's correct, but it's the only theory we have, is that, well, first we know that this magnetoreception is activated by the bird's eyes, by their retina, photons coming into the eyes. The theory suggests there is a photosensitive protein, a molecule inside the retina called cryptochrome. And the photon that comes in knocks one of a pair of electrons in one of the atoms in this protein. Remember, protein molecules are large, many, many atoms. The photon knocks one electron. These electrons are quantum entangled, right? So one's spinning up, one's spinning down, let's say. It knocks one off the atom so that it then flies off and sits on an adjacent atom, some biatomic distances quite far away. But these two electrons, for a certain period of time, remain quantum entangled. So what one does, the other one also senses. And the way they spin, whether they're spinning clockwise or anti-clockwise, which are terms that we shouldn't really use in quantum mechanics, but that's sort of the plain language trying to describe this nature of or what quantum spin is. But let's say spinning clockwise and anti-clockwise, the way they spin, the way they dance, is very delicately influenced by the Earth's weak magnetic field acting on the bird as a whole. And so the direction of the bird changes the way these electrons are spinning, spin up or spin down. and that will send signals to the bird's brain telling it what direction to go. So it's fascinating because quantum entanglement, Einstein's spooky action at a distance, many would argue that the weirdest feature of all the counterintuitive features in the quantum world, is responsible for helping the European robin find its way down to the Mediterranean. It's nice, it's a lovely story, doesn't make it correct, right? So quantum biology is still, to this day, rather speculative. Well, I got involved, interested in it, back in the late 90s. In 1997, a colleague of mine, John Joe McFadden, who's a molecular biologist, came and gave a seminar in the physics department. He's also based at Surrey. He gave a seminar in the physics department where he was suggesting that a particular biological process, something called adaptive mutations, which was puzzling biologists at the time, might have a quantum explanation. I won't go into the details, but he basically gave the talk, and most of my physicist colleagues just found it silly. It was this biologist coming and telling us about quantum mechanics. I was intrigued, and you know, I went for a beer with John Joe afterwards, and we talked about it. And since that time, for many years, he and I would just dabble. You know, we'd follow the literature such that it was, but people suggesting quantum effects in life. We would talk to other physicists who also had an interest in this field. People like Paul Davies, who's now based in Arizona in the US. I think back then he was still in Australia. Another theoretical physicist. But anyway, by 2015, John Joe, there he is, he and I published what I'm proud to say is still the only popular science book on quantum biology. In it, we started off with more established mechanisms in biology and gradually got more speculative. By the time we get to the end of the book, there's huge warning signs as to, please let's not say that quantum mechanics is going to cure cancer, because the Daily Mail would love it. Or that quantum mechanics is the origin of life down to quantum mechanics. But there were certain more specific examples, even more established than the European robin's magnetoreception. We certainly got a grant, and we set up a doctoral training centre at Surrey. That's the 20 plus PhD studentships. That's the first cohort. I'm pleased to say that my 3 PhD students have all graduated and gone on to greater things. So we started to take it seriously, is what I wanted to get across. And examining particular areas of quantum biology where we could make some progress. Walk before you can run. You see, the problem is that quantum biology is still speculative, still controversial. Physicists don't like studying the physical processes inside living systems, because living systems are complicated. A physicist likes, if they're doing an experiment, they want to do it in a lab where they can do it near absolute zero, in a vacuum, shielded from its surroundings. Spherical cows in a vacuum is the famous example, where you can tweak dials and you can control things. You can't do that in a living cell. You can't turn off certain chemical reactions and only look at a particular process. So, no thank you. Biologists didn't like it because they didn't tend to study quantum mechanics. Quantum mechanics, what a load of nonsense. Not in my lab, thank you. And then the chemists who sit in the middle say, well, all biology is chemistry in the end, and all chemistry is atoms and molecules. Of course it's quantum mechanics. Don't go inventing names for new fields just to get more funding. What's the big deal? And so you could see there were arguments from lots of, which for me is great, because it means the field remains small and niche, and one can make a name for oneself without having to, imagine, in fields in, say, high energy physics, for example, where lots of people are working in it. You are just a small cog in a very big machine. Here you can publish the papers that become the key papers in this field. So candidates for quantum effects. What were we looking at? Well, I'll give you a list. So first of all, enzyme action was something that was confirmed. So enzymes are the workhorses of the cell. They catalyze chemical reactions. They speed them up dramatically. And one of the tricks in their armory that was discovered back in the 1980s, very sort of key research at Berkeley, was that the way enzymes make and break the molecules of life, they build proteins, they dismantle molecules, One of their tricks is to use quantum tunneling to move particles from A to B, because it's a more efficient way of getting them from A to B. If they don't have enough energy, well, they can quantum tunnel through. So quantum effects were discovered inside enzymes, and that's not really controversial. Photosynthesis, well, I say well established, probably not so well established yet. So photosynthesis, one of the most important processes in life. Plants and bacteria capturing sunlight and delivering it to the reaction center in the cell, converting it into chemical energy to build biomass, right, that we then eat, so sustaining life. The first stage in photosynthesis is delivering that lump of energy, that lump of sunlight, the photon, to the reaction center. And if you only apply classical mechanics, it would appear as though that photon would bounce around like a pinball, a ball in a pinball machine, randomly, and more than likely then just lost as waste heat. And yet, with almost 100% efficiency for this stage of photosynthesis, that photon arrives at the right place. And the theory that suggests it might, the way it does that is through this idea of superposition and interference. The skier going both sides around the tree. In this sense, in this case, the photon excites electrons in the chlorophyll molecules, what are called excitons, and those can have a spread out effect over the whole cell. And only with quantum mechanics are we able to explain its efficiency. But there are still those who argue that it can all be explained using just vibrations, just classical mechanisms that don't need any quantumness. Magnetoreception birds I talked about. How we smell, again, something that relies on quantum tunneling. Again, still speculative, and I don't really have time to go into it because I want to talk about point 5, DNA mutations, which is our work at Surrey. There are other more speculative ideas, of course, where quantum mechanics plays a role in life. I mentioned connection with cancer, connection with the origin of life, and then, of course, something that Roger Penrose, of course, has been associated with for a number of years, the connection with the nature of consciousness. 6, 7, and 8 are regarded as, you know, we are not ready to say something definitive about them until we can establish quantum biology in the earlier points. So, I want to talk about DNA tunneling. It goes back to work by a Swedish physicist, Per-Olof Lövdin, who said that the DNA, double helix, so think of the DNA as a twisted ladder. The rungs of the ladder are hydrogen bonds. They're chemical bonds which essentially are hydrogen atoms. Or for me as a nuclear physicist, they're protons. I don't care about electrons. I'll leave those to the chemists. The hydrogen bond is a proton, right? And that proton can jump from one strand of DNA to the other. He suggested, he talks about this new field of quantum biology, suggesting that maybe proton tunneling might be a way that these protons get from one strand to the other. Not just by being knocked off by a passing water molecule, as you might think would be more sensible. So anyway, so we started to look at this in more detail using computer simulations. So here you have your double helix strand DNA. If you zoom in, remember the alphabet of life, you have 4 what are called nucleotides: adenine, thymine, guanine, and cytosine. Guanine and cytosine always bond together. Adenine and thymine bond together. And you can see adenine and thymine here. These dotted lines, these dashed lines, are the hydrogen bonds, the protons. And those protons tend to like to sit closer to one strand than the other. You can almost think of them like a spring that can bounce between the two. So the protons are the little white balls, and they can jump. So the blue is nitrogen and then the red is oxygen, so they can jump across to the other side. That was something was established experimentally, and this is, I'm showing here what are essentially what I was poo-pooing as the balls and sticks models of biology. I mean, that my PhD student Adam Godby assured me was generated using a huge computer code using something called density functional theory. And just because it looks simplistic, actually to get the jumping and the probability that they jump was a major calculation. What is it that's happening? How does it get across? Well, of course, we could imagine that there's the proton. So this is, remember the ball, kicking the ball up the hill. This, what's called a double well potential, think of it like an energy, like potential energy. how much, the higher up you are, the more energy you have. So the ball needs to have high enough energy to get over that bump in the middle to get to the other side, to the other strand of DNA. And it can jump over the top if it's kicked hard enough, but it can go halfway up and then just quantum tunnel through to the other side. So what we wanted to address, first of all, is how likely is it to happen? And secondly, how likely is it to happen through quantum tunneling and not just over the barrier hopping? Okay, so I'm now getting a bit technical, so that's why I can speed up. Because for many of you, it might not mean too much. There are two steps in our calculation. One is to plot what's called that energy surface, that double hump, the hump with the two wells in it. To get the right shape is absolutely vital. And we use various techniques in quantum chemistry. This was based on work back in 2021. And you can see that, right, so this is AT. Remember, AT are held together by 2 hydrogen bonds. G and C are held together by 3, but only 2 of them jump across. Imagine kicking the ball up. Don't worry about these points are not meant to sort of traces of the ball. They're just the points where the calculation has given us a number, and then we've joined the dots to give us the shape of the energy surface. And so when the proton is over here, this proton's on this side, this proton's on this side, you give it enough of a kick, it goes up to the top, but that plateau doesn't look like it's a very stable place for the proton. It could easily just roll back down again. So AT wasn't seen as a good candidate for this transfer, proton transfer. But G and C, look, if it gets up to the top of the hill and goes down to the other side, it could stay there for longer, or it could quantum tunnel through the barrier. And what we found was that this was a very likely thing to happen. How do we work out how it happens? So we've got the energy, we've got the shape. Step 2 is that's my bit, the quantum mechanics calculation. The point that when we learn about quantum mechanics at university, at undergraduate level, we tend to apply it to what are called isolated systems. The Schrödinger equations, the famous equation that describes how atoms, electrons, protons move around and interact, only works when that system is separated from the outside world. We learn that when it interacts with the outside world, that's called a measurement. You're looking at it, or the outside world is causing it to what's called decohere. But inside a living cell, you can't treat anything as isolated, so you have to use what's called an open quantum system approach. You surround your system by an environment, and essentially the environment is looking at the system. It's constantly measuring it, constantly interacting with it. Another way of saying it is that the quantum system is leaking its quantumness out into its environment. For the technically minded, what we solve is a master equation. There's a famous one called the Caldera-Leggett model. There are more sophisticated approaches, but that fitted our purposes for now. So what we were doing was essentially cranking the handle for this equation to see how that proton travels through the barrier or over the barrier. So we found there's a very large probability. The tautomeric occupation means the chance the proton's on the other side. For G and C, 1 in 10,000 times. If you were to look at just a pair of these bases and you could take a photo of them, 10,000 times, 10,000 snapshots, one of those snapshots, the proton will be on the wrong side. That's a lot. And also the fact that so this is a plot against temperature, right? So this vertical line is the temperature of living systems, around about 300 Kelvin. And you can see that if you only allow the protons to go over the barrier, then you've got a 1 in a billion chance that it'll get to the other side. But if you allow quantum tunneling, then most of this 1 in 10 to the 4 is down to quantum tunneling. And so it's very likely to happen. Now, what I didn't mention is, why is this at all interesting? Well, this goes back to Lövdin's paper in the 60s, because he said DNA, the hydrogen bonds, the protons can jump from one side to the other, so what? And they might jump back again, if they don't like life on the other side. But DNA gets unzipped in the process of replication. It enters a particular enzyme system called a helicase, and that helicase is like a zip fastener being unzipped, and the two strands are separated. if they're separated and that proton, or both the protons, because one moves, the other moves, if they're in the wrong position, then in the process of replication, A will not bond to T, and T will not bond to A. They will bond to a different base. What this means is a mutation. Okay, so if the proton's in the wrong place, that can lead to a mutation. So it was very interesting, and even Crick and Watson thought about this idea. Maybe, you know, if a proton can transfer from one strand of DNA to the other in a hydrogen bond, that could lead to a mutation. Now, clearly, we know how often mutations take place. We know that mutations are very important because without them, life wouldn't be able to evolve. We also know they can be very dangerous because we don't want the coronavirus to mutate away from something that, you know, our drugs can attack. But we know mutation can take place in all sorts of ways. Ionizing radiation, copying errors, you know, there's lots of mechanisms. This is another one, proton tunneling. And it seems to be far more than we see. So what's happening? One thing to say is that we have an open system, and so the surrounding environment inside the cell is causing decoherence. The water molecules that the DNA is floating in, they're constantly observing the system, causing it to decohere. But it doesn't completely decohere. You can plot to what extent your quantumness has disappeared, has dissipated. To what extent has it decohered and the information has moved out. There's a measure in quantum mechanics called the von Neumann entropy, which is a number that we can calculate that tells us how much quantumness is left in the system. And what we find is that actually, although if you ramp up the temperature, the temperature, this is the temperature of the water surrounding the molecule, right? The environment's temperature, the bath. If you ramp up the temperature, then the von Neumann entropy goes up, the disorder goes up, and quantumness disappears and decoherence sets in. But at living temperatures, 300 Kelvin, there is still quantumness. There is still quantum tunneling taking place. What's interesting then is what happens when you unzip the DNA. What we found was that, so clearly here, when the DNA is at thermal equilibrium and not being unzipped, and it's just quite happily minding its own business, this is what the potential energy surface looks like. There's a 1 in 10,000 chance the proton will be on the wrong side. Fine. But what happens when they unzip? Because, of course, as they separate, it becomes increasingly harder for the proton to jump across. The two strands are further and further apart. The energy needed is higher. The barrier gets higher. Do you trap the proton in that place that you want, or does it roll back again? What we found, in fact, that something very clever seems to be taking place inside the helicase system. There's a particular enzyme called asparagine, which it does the unzipping. It sits right at the entrance, right at the point where the two strands start to separate. And what it does is change the shape of the potential energy that the proton is feeling. So this dip here disappears. What happens then is that most of the protons that were in the wrong place, the 1 in 10,000, which is still a large fraction, roll back down to the original position. And so the question became, we were wondering whether life has the ability to use quantum mechanics to its advantage. Can it, in enzymes, it uses proton tunneling. Enzymes use proton tunneling to their advantage. And one can argue that life has had 4 billion years nearly, and it's evolved the ability, just through random selection processes, to make use of quantum mechanics. And why wouldn't it? If it finds a way of making some process more efficient, whether it's classical mechanics or quantum mechanics, life will use it. What we're finding here is that it seems that life knows that quantum mechanics would cause a lot of mutations. And so the organisms where lots of mutations are taking place due to quantum tunneling, clearly they didn't survive. They didn't do very well. But those that had this enzyme here that changes the rates of mutation, the rate of tautomerization, those are the ones that survive. So life knows about quantum mechanics and it mitigates against its worst excesses. I'm going to do something really awful here because I know I don't want to go over, and I'll give you time for questions. I'm going to skip over the measurement problem of quantum mechanics. Essentially, the measurement, Schrodinger's cat in the box, and there are different aspects of the measurement problem. The first two are solved by decoherence. The third one, the problem outcome, requires an interpretation of quantum mechanics. So, for example, just two of the more popular interpretations of quantum mechanics, spontaneous collapse models, would say that the cat is. It's not that when decoherence takes place, the cat is either dead or alive, and it's just our ignorance. No, both the dead and alive situations are there. It's the cat dead and alive at the same time that's got decohered away. But you need an interpretation to choose one outcome. And spontaneous collapse models would say one of them disappears and the other remains. An Everettian many worlds interpretation will say that neither disappear, you just find yourself in one universe or the other, with either a dead cat or an alive cat. But the point is that what's happening inside the helicase seems to be a bit like Schrodinger's cat in the box. You've got your water molecules, which is the environment, which causes partial decoherence. So you can think of the proton being in both positions at the same time, or more likely as some spread out wave function, smeared out across the whole bond. But then as the strands separate, the helicase is the observer. The helicase is Schrödinger opening the box, or more correctly, actually the cat, because the cat knows if it's dead or alive. Right? It's not. You don't need someone to open the box to tell it. The cat's perfectly capable of causing decoherence, very macroscopically distinguishable states. Okay, so here it's the helicase that not only makes the measurement, but it also adjusts things. It makes sure that the proton isn't in the wrong place. Most of them are in the right place, and then it does the measuring. Okay, so the conclusion is that when it comes to quantum tunneling DNA, it's not that life uses quantum mechanics to its advantage, but it knows about quantum mechanics and has evolved mechanisms to prevent things happening that would damage life. So does life use quantum mechanics? I would argue yes. We are starting to see evidence for it. And we're also starting to see evidence that life, if it doesn't do something about things, the quantum mechanics can be damaging as well. Either way, life seems to have evolved the ability to use some of these trickery of the quantum world. And I will end there by thanking my collaborator, Marco Sacchi, is a computational chemist that I work with at Surrey. Max Swinoken is my PhD student. He's just submitted his thesis. Louis Slocum's an ex-PhD student who's now a postdoc working with us. We get our claws into the smart guys, and we don't let them escape. And I think I should end there because I've now talked to 3 minutes past 6, and I was hoping we'd have time for just a few questions. So thank you very much for your attention.